Good day everyone, I welcome you back to the Education Zone. And today in this particular episode of our Crash Mathematics or Further Mathematics course, we are going to be dealing with a subject called Further Mathematics today, and this is the first episode of course. And in this first episode we are dealing with a topic called sets. Now what about sets? Sets is a very important topic in Further Mathematics because it involves the application of different concepts. Like even when you have to go to university level mathematics, you will still do what is known as set theory. And sets, as it is, it's a very important part because it's a kind of aspect of mathematics that can be applied in the real world. So as we discuss, I will show you some real world application of sets. We'll be doing some questions, we'll be addressing some problems in mathematics, and then you will see why I said set is a very much applicable subject. So now let's start from the first concept here. Now the first concept we're dealing with here is we're going to be dealing with first we have performance objective. Yes, we do have performance objective. So the performance objective of this course is to make you to be able to define what a set is. So I want you to be able to define what a set is, and then you should be able to represent it in a Venn diagram and do a couple of things with set. So when we talk about set, a set can be defined as a collection of well-defined objects. So when we talk about a collection of well-defined objects, they are kind of like a container that contains some objects, and those objects, they are in consideration. They are very important for us to consider. So like a set of mathematical instruments. In your mathematical set, you have instruments like your ruler, your protractor, your compass, your name it, your cleaner, your divider, and so on and so forth. So those are elements of that mathematical set, right? So that's kind of like a real world abstraction of what a mathematical set means. So starting from the basics, we are going to be talking about the definition of set, which I've talked about, but we'll still be talking about it again. So when we talk about a set is something we are much familiar with by now. Many of us are familiar with sets. For example, when we go to school, you talk about set of students who graduated from your own year. So when I was in secondary school, the particular set of students that graduated with me along me in the same academic year, we called ourselves the 20-something set. So you can also say it's kind of like a particular collection of students. So in that case, you can just say a set a collection of anything that you want to group together. You can say a set of kitchen utensils, a set of bicycles, a set of equipment, and so on and so forth. There are different collections that can form a set. So, but basically, let's understand that a set is a collection of items. So we can define a set in three ways. You can say it's a collection of books in a public library. So these are examples of what you can call a set. You can also call it a collection of tools in a factory shop. You can call it a collection of items in a mathematical set, and so on and so forth. So there are different things you can call it. So that is something you should understand. Now let's talk about another concept. A collection of books in a public library, as you know it, is for example, it constitutes a set, right? And each member of a set is called an element of that set. So when we talk about a member of a set, is those kind of members are called elements of a set, and these elements of a set, they are the materials, the component, the constituent of that particular set. Now let's move on to something else. We'll talk about finite and infinite sets. Now what about finite and infinite sets? A finite set is basically a set that has a completely definable set of elements. So let me come again. A finite set is a set that you can be able to define all the elements of that set. For example, if we say the set of states in Nigeria, that set will consist of only 36 elements. So those elements stand for the 36 states of Nigeria, right? And so that goes for every country. Every country in the world has a finite set of states, of whether independent and dependent, whatever you want to call it. So every country in the world has a finite set of states, and that is what we call a finite set. If we are going to categorize it into a mathematical set, right? So, but when the number of elements in a set is kind of endless, like it goes on and on and on, and you don't know when it stops, it's called an infinite set. Now, this concept of finite and infinite set, they are concepts that we are going to be taking further and further into this course. In this channel, my major focus is getting you guys to understand mathematics practically and pragmatically. So that means we are going to be continuing to do courses like this, and in future I'm going to be doing a course on engineering mathematics, and depending on your demand, if you guys ask me to do a course on advanced mathematics, I will learn the skill and get it done for you guys. So it's just based on your feedback, but I will need feedback on the kind of course that I should be doing in this channel, so that I'll know which one will match the greatest returns for me. So basically, that's just the point. Now we've talked about finite and infinite sets, right? That's the concept for today for finite and infinite sets. Let's talk about something else. So, but next time you are asked what a finite set is, just say it's a set whose elements are limited. But an infinite set is a set whose number of elements are unlimited. For example, let me give an example of infinite set. Example of infinite set is a set of positive numbers. So that will start from 1 to 2 to 3 to 4 to 5 to 6 to 7, and so you get to 100, you get to 200, you get to 1 million, 1 billion, 1 trillion, 1 quadrillion, and so on and so forth, and it never ends. So that is kind of like an infinite set. It keeps going on. Nobody knows when it ends. So, but in mathematics, when you get to advanced mathematics, there's what is known as the convergence and divergence of sets. So, but we're not talking about that today. That will be kept for our future course in probably engineering mathematics. So let's talk about something else in sets. So I want you to understand that this is basically the foundation of sets. I'm setting the foundation for us here. So then let's talk about subsets and supersets. So what about subsets and supersets? It's basically a concept where we talk about the fact that some sets they consist of other elements, while some sets they contain other elements. So basically, let me explain myself. When you say something is a subset of another set, you are talking about the fact that that set is limited inside another set. You get it? So kind of like if you are saying Ibadan is a subset of Nigeria, that means Ibadan contains a number of people that are also in Nigeria, but Nigeria also contains other people. You get it? So it's a subset. But if we say Nigeria is a superset of Ibadan, that means Nigeria contains other elements along with the elements in Ibadan. So you get it? So for those of you who might not be in Nigeria right now, you can also use this as an analogy for your country and your state. So depending on the state you are in, you can say your state is a subset of your country, and your country is a superset of your state. So that's the best way to explain this concept. So, but from what you can see on the screen here, I'm assuming that there's a display right now, and in that display you can see that subsets and supersets. We can see an explanation here, right? Consider the given set, two given sets A and B. Yes, if the set A consists of some or all of the elements of set B, then A is said to be a subset of B. You get it? So if A consists of some or all of elements in B, it's called a subset. So mind you, if that set A consists of all the elements in B, it's called a proper superset. So it's called a proper, rather a proper subset. But if set A does not contain all the elements in another set, so it's just called a subset. And there are notations for this. Let me give you one example of notation. So one notation for a subset we could do is basically we could use if you want to say A is a subset, you can say A is, you can use this subset B. So this is trying to show us that A is a subset of B. So I'm assuming that you guys can see the board right now. Okay, let me get it somewhere. A is a subset of B. So this is notation for subset. A is a subset of B. And then when you talk about supersets, it will be A to B is a superset of A. So basically this means that if A is a subset of B, that means B will be a superset of A. So that's kind of the natural conclusion. If A is a subset of B, then B is a superset of A. So the notation for subset is C with a dash underneath it. Then the notation for superset is an inverted C with a dash under it. So that's A is a subset of B, B is a superset of A. That's one concept you need to grasp for you to understand this concept of set and superset. So now let's move on to something else. And the next thing we're talking about in this video we'll be talking about something a little bit beyond subset and superset, and that would be on equality of sets. So basically, one thing about equality of sets has to do with the concept that a set is equal to another set. So when you talk about that equality of set, it's all in the elements. For example, Nigeria is equal to Nigeria, right? It's even equivalent if you like. So basically, when a set is the same thing as another set, or when a set contains the same elements of another set, they are both said to be equal. So let me repeat myself. For example, if you were given 5 oranges and 3 apples, and you put those in a bag, and then we say that bag is a set, and then I was also given 5 oranges and 3 apples for the sake of equality. Yes, so we'll say those sets, they are equal because they both contain 5 oranges and 3 apples, right? Even if your set is called A and my set is called B, the name does not matter in the equality of sets. What matters is the quantity and quality of elements in those sets. So, and even if you have a repetition of elements, which you will in the next few minutes I will explain that. Even if you have a repetition of elements, it still doesn't matter because that that quantity of sets is still valid. So if you in sets, if a particular set A consists of elements, so there's a set notation, and the set notation is use of curly brackets. So make use of curly brackets for the set. So curly brackets. So if A is set of A, small letter A, B, small letter B, and small letter C, and then we have B is the set of, so we have the curly bracket, and then set of A, B, and C. Now these two sets, they are not they are equal. They are equal because they still have the same quality of elements. For example, there are times when the quality matters and there are times when the quantity of elements matter. For example, when I'm talking about the cardinality of a set, that is when the quantity will matter. But when I'm talking about the equality of a set, we will need to consider the value of quantity of quality. So that means even if you have a repetition of your elements, they are still equal because they still have the same quality of elements. But then when we talk about quantity, there's what is known as cardinality of sets, which we'll be talking about very soon in the nearest few minutes. So I hope you understand the concept of equality of sets. So let's talk about something else, which is the concept of the universal set. So basically, when we talk about the universal set is a set that consists of every other set in consideration. So a universal set is a set that it consists of every set. It covers every set we are talking about. It covers every single set in the consideration. In mathematics, for example, if we have the earth as a universal set, that means we are trying to say that the earth consists of all the countries in the world, and each of those countries, they are subset of that universal set. So every other set in consideration is a subset of a particular universal set. So you understand that concept now. So then we'll talk about the universal set. We have the notation for universal set, which is the stylistic U in italics. I assume there's a screen on there's a notation on the screen right now. So and then you have a set which consists of only one element. It's called a unit set. Okay, that's also compulsorily true. So we have other concepts like that and so on and so forth. So there are different things you need to understand about this concept. And that was for universal set. Then we also have the unit set and empty set. So basically a unit set is a set which consists of only one element. Then an empty set is a set which consists of no elements at all. So we have the annotations for these unit sets and empty sets. For example, you have the unit set, and then we also have the empty set. So there are two ways of representing an empty set. So I'm aware that the top of the board is not very clear right now, and that is because of the improper lighting. So actually, for this course, from the next episode, I will try to edit the location of this video to make sure that the lighting is appropriately level for the board to be seen. So next, let's talk about the notation for empty set or null set. So the notation of empty set is you have a circle and then you can just have a strike through it. So that's the notation for empty set. Or you can make use of two curly brackets with nothing in between them. That means you can use either of these two methods as notation for an empty set or null set. So that being said, let's move on to something else. So I hope you are enjoying this course. If you are, don't forget to like, share, and subscribe to this channel because this is the kind of teaching you will not get. Even when you are in school, you might not be able to have a one-on-one teaching like this. So I encourage you to subscribe, like, and share, and continue to watch these videos of this channel because I'm here to educate you for your own good. Next, let's talk about something else. Let's talk about the cardinality of a set. So let's talk about the cardinality of a set. I want to talk about the cardinality of a set. Cardinality of a set has to do with the fact that a set consists of a number of elements. So basically, I was given some examples before. The cardinality of a set is the number of elements in that set. So, for example, if you have a set on the screen, for example, the set A on the screen, you can see that it consists of 4 elements. It consists of the elements A, M, B, and D. So basically, the cardinality of that set is 4 because it consists of 4 elements. So that's basically what I want you to understand here. That's what we will call the cardinality of that set, the number of elements in that set. So consider the set A, which is the set of elements A, M, B, D, and H, right? So now there are 5 elements in the set, right? Obviously, and the number of elements in the set is called its cardinality. So you understand that concept now. So for example, if I say how many elements, what is cardinality of Nigeria? So in my country, Nigeria, we have 36 states in this country. So that is excluding the Federal Capital Territory. Now, each of those 36 states, they are elements of the set called Nigeria, right? So that means we are going to say the cardinality of the set called Nigeria is what? 36. That's simply as simple as possible. Now, I am very convinced that you understand that concept. If you do, if you don't, you can rewind this video to listen to it again. Let's move on to something else. Let's move on to and there's a notation for cardinality of the set. Cardinality of the set is denoted by NA. You can see it on the screen here. And then hence in the given set A, NA is equal to 5. So that means the N open bracket A is equal to 5, and that's the notation for cardinality of a set. So that's the concept for cardinality of a set. But at that rate, let's solve an example. Here we have an example 8, and we're asked to determine the cardinality of each of the following sets. So the cardinality of each of the following sets, and let's have some sets on the screen now. So basically, we have some sets on the screen, and then this set we have set A, which is number 1, Roman figure 1, and it is given as a set of B, E, F, B, A, T, F, G, and X. Then we also have the set H, which is the set of A, B, which is the set of the set A, B, or rather the tuple A, B. Then okay, for those of you who are not into programming, actually spare me that, because but if you are into programming, you have an advantage of understanding what tuple means. So basically, you can see that in that figure 2, the set H consists of tuples, and those tuples, they are elements of that set. So you cannot begin to count them one by one. You count them tuple by tuple, right? So that means this element H consists of tuple A, B, and then tuple E, F, and then tuple G, K. So that's the difference. So for that element, for that set H, we would be saying it has a cardinality of 3. It has 3 elements. Next, we go to set G, which is marked for 3. Then we have 2, 3, 56, and 9. So it also has cardinality of 4. You can see the solutions there. So and then lastly, you have for 4 the set T, which has a cardinality of 0 because it is a null set. So that is the notation of null set. So that notation is not very accurate, but it's close. I've given you the notation on the screen. You can check the screen. Now the notation of a null set is right there on the screen. So it was given as this. The notation for a null set. That's either this or this. A circle with a strike through it, a diagonal strike through, and then or you can use 2 curly brackets with nothing in between them. So I hope you understand that concept. So following that, I would want to give you guys an exercise, which is probably on the screen right now. You can try it. But if there's an exercise on the screen, you can just continue playing the video. But if there's an exercise on the screen, you can just pause the video and attempt it. There's an exercise on sets which I want you guys to try. So that's exercise 1A. Next, let's move on to another concept in further mathematics. I hope you're enjoying this course. If you are, don't forget to give this video a like, share, and subscribe. Thanks. So let's talk about something else. We're talking about intersection of sets. Now I know that you guys are oriented towards calculations, but before we do any calculations, let's first of all understand the basics, right? So the intersection of sets. So what is an intersection? The intersection of two sets is a set which consists of the elements that are in A as well as B. So basically, on this screen we have that the intersection of two sets A and B is a set which consists of elements that are in A as well as B. So basically, it's kind of like what we share. What are the common properties that those two sets share? That's called an intersection. For example, if we have Nigeria as a country, and Nigeria consists of 3 ethnic groups, and then we have the Hausa, the Yoruba, and the Igbo ethnic groups in Nigeria. And you also have another country which also consists of one ethnic group that is also in Nigeria, maybe something like Igbo or so. So those two countries, they share the same ethnic group. So if we were to look for the intersection of those two countries, their intersection will be the ethnic group that they share in common. And the same goes for every other thing in mathematics. For example, if you are given an orange and an apple, if you are given an orange and an apple, and I'm giving a let's say an orange and a banana, so that means they both give us oranges, right? That means we both share oranges. That is our intersection. So you understand that concept. But then we want to talk about let's give an example. In this example, we have that let r is equals all positive even integers less than or equal to 20. Q all factors of 20, then r equals 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So basically, these are different kind of sets, and you can be asked questions like this. Look for the intersection of sets. So in this case, all you need to do is you just look for the set, the elements that will be common to both sets. But let me give you a snippet of what you will be able to, the conclusions you'll be mostly be arriving from here. One of the conclusions you'll be arriving from here is that you will notice that most of the time sets of odd numbers and sets of even numbers, they do not have an intersection. So if two sets don't have any intersection, they are called disjoint sets. So that is disjoint sets, and they don't have they don't have any intersection. There's nothing common between them, so they are disjoint. So I hope you understood that concept of set. Let's move on to union of sets. So union of sets. When we talk about union of sets, we are talking about the fact that it's a union of two sets is a set which consists of elements that are either in A or B or both. So basically, when we talk about the union of two sets, there are elements that are either in the first or in the second, or they are in both. So for example, if you have two sets as, for example, based on my previous example, if you are given an orange and an apple, and I was given an orange and a banana, then the union of everything we have will be orange, will be your orange and your apple combined with my orange and my banana. So in mathematics, we will say that consists of three different distinguishable elements. Because if you have an orange and I also have an orange, that means we are sharing the same orange. In mathematics, that only counts as one element. It's not repeated, except when you are talking about the cardinality of that set. So that means our union would be orange, apple, and banana. Not orange, orange, apple, and banana. No, you will not mention any elements twice. Only once you will mention elements. So that concept, I hope you understand it. Let's move on to an example on set. So you have the example 11, given that G is equal to H, E, A, P. H is equal to L, A, K, E. Then G union H equals what? That will be basically the union of all the elements in those two sets. That will be you'll be given the union of the elements in G and the elements in H. That will be G is consists of H, E, A, P. That's H, E, A, P. Then plus the elements that are distinguishable or that are also in H. So we will not include we will include L because L is distinguishable. It is not found in G. So we will not include A because A has already been listed in G, so we will not mention elements twice. So always remember that when you are combining elements, you don't need to mention them twice. Then we also have the K. We will mention it since it's not repeated. Then the E we will not mention it since it has already been mentioned in G. So the intersection will be H, A, P, L, K. So you can try example 12 and look at how it goes. That's the concept. Now let's move on to something that is basically I consider the one of the most important part of this course, of this episode, and that will be Venn diagrams. So what about Venn diagrams? Venn diagrams are sets can be represented diagrammatically by closed figures. So and this method of set representation was developed by John Venn. So and I guess that was I guess maybe the 16th or 17th century or so. Then the Venn diagram, what's the Venn diagram? It's basically a pictorial representation of sets. And the operations of sets can easily be demonstrated by using Venn diagrams. So Venn diagrams, they are basically pictorial representation of sets. And this pictorial representation, they help us to understand what we're actually trying to represent in practical terms. For example, your set of oranges and apples can be represented on a Venn diagram, and my set of oranges and bananas can be represented on a Venn diagram. Then there will be a common area, and that common area will be an intersection. Then there will be an uncommon area, which will be or let's call it a peculiar area, and that peculiar area will be the non-intersection. So that's for that. So basically, There are different classes of Venn diagrams we'll be dealing with, but let's talk about the different kinds of Venn diagrams we can talk about. Yeah, so we'll have different types of notations for Venn diagrams. For example, let's talk about the intersection. Okay, now this kind of intersection is basically formed when two subsets have one or more elements in common. So now in this diagram on the screen below, so you can probably see something on the screen, and this diagram on the screen, it is representing the rectangular part of this diagram is the universal set. Then the two circles, they are both subsets of the universal set, but they have an intersection, which is the shaded area in between them. So we have the set A and set B, and then there's an intersection between them. So set A and set B intersection, and that intersection is their union. Rather, it's their intersection, rather. So that was for intersection. Let's go on to talk about something else. That's what's called again? The complement of the intersection. So I might not have talked about complement earlier, but the complement of a set is a set that contains every element that is not in the original set. So let me come again. For example, let's say you have an annoying friend and that friend does not want to have anything to do with you. So that means the friend always gets the kind of shoes that you don't have. So he comes to your house and any shoe he sees you have, he will not buy it. He will buy the shoes you don't have. Kind of wants to annoy you and infuriate you. So that is basically what we call a complement. A complement of a set is a set that contains all the elements that are not in the original set. So that complement is so careful and make sure that it does not contain any elements that are in the set you are considering. So in this diagram we have the elements, the complement of the intersection of set A and B. So you see that middle area that was once shaded, now it has become white, and now the original shaded area is now the exterior part of that middle area, because it does not want to have anything to do with the middle area. That's the complement of the middle area. And since the middle area is the intersection, that is A intersection B, that means the complement of that middle area is denoted by open bracket A intersection B close bracket complement. So that complement is a small dash above the bracket after the closing bracket. So yeah, you can see that on the screen. So A intersection B complement is the shaded part shown. Next we also have the A union B complement. So basically you can see that this A union B, just as I mentioned earlier, it consists of anything that is not in the union of A and B. So it consists of the union of the universal cells that are not neither in A nor in B. That's complement. So complement consists of anything that is not in the set. Complement of the set consists of any elements that are not in the original set. Then we also have the another concept. We have intersection of two sets. So the intersection of two sets is the union of two sets is a third set, which consists of the elements that either are in A or B or both. So on the screen here now, you have what is displayed on the screen now? You have a union of two sets. So this union, you have the set A uniting with set B. So the shared here consists of everything in A and everything in B all together. So that is the concept we are going to be dealing with. Then let's also talk about something else. So I hope you understand. Let's talk about something else. Let's talk about the set itself. So the set itself, that's without any union or intersection. So we have A complement. So that complement of the set itself consists of the area of the universal set that is not in that set. So you can see that every part of A is not shaded, while every part of A that is outside A is shaded. So that is the complement of the set A. Then let's talk about something else. We have the which is another part of this video, which is we have the A alone. So I like calling it A alone because it's the only part of the set that consists of only A. So I call it A alone. Yeah. So in this diagram, you can see that this part of the Venn diagram, it's a region that consists of only A. There's no part of B inside. So it's excluding B. So that is called A intersection B complement. That's the shaded part shown below. A intersection B complement. So these are all Venn diagrams. So these are all Venn diagrams, and these are the notations that we commonly use in Venn diagrams that involve two sets. So we're also moving to three sets. There are also four sets, there are five sets, and so on and so forth. But the greater the number of sets, if you add one set, the difficulty of the question increases. Let's call it geometrically as the number of sets increase. So basically, for 2 sets, you have 4 possible regions in the 2 sets. But for 3 sets, you have 8 possible regions. So basically, the number of possible regions is equal to 2 raised to the number of sets. So for example, if you have 2 sets, the number of possible regions you can get is 2 raised power 2, which is 4. But if you have 3 sets, the number of possible regions is 2 raised power 3, which is 8. So it's kind of like an exponential increment. Not really exponential, but it's quasi-exponential. You get it? So that concept is something you need to understand. Let's move on to something else. Where we're talking about the subset. Yes, I was explaining subsets earlier. So the subset of a set is a set that consists of that is contained in that set. So for example, in this diagram here, you can see that we have a circle inside another circle. So this circle, the circle B is contained inside the circle A. So it is kind of, you can say the circle B is a subset of circle A. So that is basically what we know it as in mathematics. Then we also have the supersets. So basically, one thing about the superset is the superset of a set is the set that consists of that original set. So for example, in the previous picture, you will notice that set A is a superset of set B, while set B is a superset of is a subset of set A. Then here we have the B only. I like calling it B only because it consists of everything in B but nothing in A. So it is A complement intersection B. So just know that the set which you are not referring to, we have the complement. So for example, we are not referring to A in this diagram yet. So that means everything in A is not shaded. That means we have the complement over A, which shows that it is not A. Complement means not that element, not that set rather. So I hope you understand that concept. And so far, I'm glad we are progressing very fast in this course. And I hope you are enjoying this course. So let's move on to something else, which is an example. So in this example, we are going to be dealing with an example on 2 sets. So we have a survey carried out on 15 adults showed that 8 of them smoked cigarettes, while 10 of them said they drank beer. Find the number that smoked cigarettes and those that drank beer, if each of them did at least one of the 2 acts. So in this case, in this question that is shown on the screen, you have a survey. So in the survey, it was shown that it was a survey carried out on 15 adults, right? And showed that 8 of them smoked cigarettes, while 10 of them drank beer. So we have to find the number that smoked cigarettes and those that drank beer, if each of them did at least one of the 2 acts. So at least out of those 15, they are either smoking cigarettes or they are drinking beer. So we are looking for the number that smoke both, that they belong to both categories. So that means those that both smoke cigarettes and drink beer. So in this case, this is a mathematical question that involves sets, and it's as simple as possible. All you need to do is define your regions. For example, in any question you are given in sets, you need to first of all define your universal set. So here we say let U equals all, that universal set U equals all adults that we interviewed. So this is a set of all adults. Then also we have the set S, all adults that smoke cigarettes. Then also have the set D, all adults that drank beer. So all you need to do is you start from the basics. For example, you know that the number of elements in the universal set will be what? Can you guess? That means all the adults in consideration. That is 15. There are 15 adults in consideration. Then we also have next. We also have the for the question we have that 10 of them drank beer. So that means the number of elements in set D will be what? Right. 10 of them said they drank beer. Yes. Then we also have that will be 10 in set D. That's the cardinality of set D is 10. Then next we have the cardinality of set S is 8. So when we do the calculations, you will know that from your knowledge of mathematics that inverse set consists of every element. So that means when you add all the elements together, you must get the inverse set number of cardinality of the inverse set, which is 15. So that means we have 15 which were in the inverse set. So that means assuming the number of people who both smoked cigarettes and drank beer, assuming we don't know that number, we can just call it X. So that's why we say it in the next line of the equation. We have let n S intersection D equals what? X. So you can now say that the number of people who did both is X. Then the one who did who smoked will be 8 minus X, because that means those that smoked only will be the total number of people that smoked. That means those that smoked only will be the number of people that smoked and drank, subtracted from the total number of people who smoked. That means you want to get people who smoked only. And for example, that would be 8 minus X. Then also have the number of people that drank beer only. That would be the total number of people that both smoked and drank, subtracted from the number of people that drank. That will give you the number of people that drank only. So that's 10 minus x. And then when you add up all the regions together, there are 4 regions here, but the last region is 0 because they said every one of them did at least one of the acts. That means the region that is excluding all of these regions will be 0. So from this, when you do the calculations, you have 8 minus x plus 10 minus x plus x equals 15. Then at the end of the day, when you solve the equation geometrically by calculation, by algebraic calculation rather, not geometric, algebraic. When you solve it algebraic method, you get x equals 30. So that's something that is quite simple to understand. Now let me remind you, actually this course in further mathematics is going to become more difficult as we progress. So this course, I'm devoted to this further mathematics course. We are going to be doing a lot in this course. So if you still don't understand basic concepts in mathematics like algebra and so on and so forth, I advise you you check out the playlist on mathematics in this channel. So there's a course on mathematics, on normal mathematics. You can watch that course first. Probably maybe the one of the 3 courses. There are like 3 or 4 courses on mathematics. You can watch them before getting to watch the courses on further mathematics. So that is what I'm trying to say here. So basically we exhausted that concept. So next, let's talk about something else. Well, I hope you understand that concept of. So let's talk about power set. So power set is the set of all sets of a particular set. It looks confusing, sounds confusing, right? So basically, from the diagram you can see here, you have the set of all subsets of a particular set X is called the power set of the set. So that means it is the set that consists of all possible combinations of the subsets of that set, or rather all possible combinations of the sets of the elements which are called subsets. So if you combine the elements of a set in different ways, you will get subsets. That's what I need you to understand. So in this case, for example, let's say if x is equal to a, determine the power set of x and the cardinality of power set of x. So in this case, let's say x is a. That means the power set of x will be equals to, will consist of, whether you pick nothing, which is the null set, that will be null set, comma. Then if you pick a, that will be the element a. So a power set is a unique set that consists of all the possible combination of elements of a particular set, which is called the subset of that set. So next, when we calculate everything, we'll get the cardinality of the power set is 2, which is consists of either nothing in the set and then everything in the set. That's the cardinality of that set. So having covered that concept, I hope you understand that concept, and hopefully if you do, we are free to move on to the next part of this video. So if this video is getting long, yes, that is expected, that is anticipated, it is not naturally supposed to be so. Then let's talk about classification involving 3 elements. So one about classification involving 3 elements of a set, but then about the fact that 3 sets, yes, 3 sets. Let's call them 3 elements of a universal set, but they are those elements, they are sets in their own right. You get it? So if we are classifying involving 3 sets, we are going to be having 3 different regions on that set, and then the number of different combination of that regions will be 2 raised to power 3. That's 8 different regions. That means we're having 8 different regions. So you can see that it increases greatly. We are dealing with 8 more regions, 8 different regions as well as we progress with this set. So let's talk about the different region combinations of a set. So first region combination we're talking about here is the intersection region. So when we talk about intersection region, we're talking about the fact that on the screen here you have an intersection here, and that is denoted as A intersection B intersection C. So that is the region that is consists of, that is a part of A, it's also a part of B, it's also a part of C. So in this region, that shaded region at the center spot of that universal set is called the intersection of those 3 elements of the set, or those 3 subsets of the universal set. So let's talk about the something else, and that's that is the concept of A intersection B complement intersection C complement. That is A alone. So you remember I told you earlier that when you talk about a set alone, it's basically you are going to add complement to the remaining sets. So that will be A alone. So A intersection B complement intersection C complement means A alone. And in the same vein, we also have A and B, A intersection B. That's That's basically A intersection B intersection C complement. That means you are saying A and B alone. That's simply what you're trying to say, A and B alone. So basically, then we also have the B alone in this case. So that's basically A complement intersection B intersection C complement. That's B alone. So you answer the only region shaded here is B. Then next we also have the B and C alone. So that's the intersection of B and C, and you can see that in this region it's only B and C, the intersection of B and C that is shown. So A is not part of the diagram shown. Then you also have the C alone. So in this case you have only C that is shaded here. So that means we have it as you are shading only the region that contains the set C. So the set A and B are excluded. That's why you have A complement intersection B complement intersection C, and so on and so forth. There are many different combinations of these elements that we'll be dealing with. But I hope from this background knowledge that I've talked about, you should be able to have a fundamental knowledge of this combination of regions. See, with those regions that you understand now, there's nothing else that will be giving you issues. So we can move on to then complete this course. So I guess you understand the fundamentals of these regions of the set. So if you don't understand, you can still go over this video. This video was carefully made. I try my best to cover the concepts in such a way that you will still be able to grasp it no matter your level of knowledge in further mathematics. So now let's move on to the conclusion of this episode. So for those of you who had the patience to stay to this time, we have a summary of everything we've talked about today. And this summary we've talked about the sets. So you can just go over the summary on the screen, tell the summary, and then you can revise the fundamental concepts in this video. So far I hope you've enjoyed this episode, and thanks for watching.